Good morning. I'm assuming that you have watched the brief video on what the mole is, and we're going to actually start working on moles number 1, which will walk you through some of the basic ways that we use the concept of the mole. So before we get started, make sure you have moles number 1 opened. Make sure you have a copy of the periodic table. Remember, ptable.com is great as well. And make sure that you have a calculator. So those are the 3 things you'll need: moles number 1, a periodic table, and a calculator. So let's go ahead and look at what you're going to have to be doing for moles number 1. So here you can see moles number 1. And the first question is, what is the molar mass of uranium? Now, when we use the term molar mass, that simply means the number of grams in 1 mole. So in order to ascertain that information, we simply, you see our very first question says, what is the molar mass of uranium? So for 1A, we want to know the molar mass of uranium. So we simply find uranium on the periodic table, and we find its average atomic mass, which is 238.03. And so we'll say that the molar mass of uranium is 238.03 grams. Notice that I simply used the molar mass for uranium, and then I added the unit grams. That's a molar mass. There are 238.03 grams of uranium in 1 mole. Remember that this number also represents the average mass of 1 atom. Now, uranium has several isotopes, but if we took the average mass of 1 atom of uranium, it would be 238.03 atomic mass units, AMUs. Right now, though, we're using the molar mass. That's a way that preserves the mass ratio, but is a reasonable amount to handle in a lab setting. So go ahead and get the molar masses of these 6 and make sure you number them and write those down on your sheet of paper. Remember, you're just finding them on the periodic table, finding their average atomic mass, and then writing it with the unit grams. Pretty straightforward. So pause and do that. So what did you do when you got down to 1D? 1D is oxygen, and oxygen exists in nature as a diatomic molecule. In other words, 2 oxygens are bound together. It's found that way in nature exclusively, except for occasionally you'll find it as ozone, which is O3. So what did you do for this? Well, if you look at the atomic mass for oxygen, it's 16. So what would you guess you do for O2? Yeah, you take 2 16ths. So for oxygen, you should have had 32.00. If you don't have that, take a second and fix it. And don't forget to include the unit grams. That's what makes it the number of grams in a mole, or the molar mass. So once we get past the atoms, what might you guess we do when we're trying to get the molar mass of a compound? Well, all we do when we're trying to get the molar mass of a compound is add up the molar masses of all the individual atoms. So for example, on 2A, we're supposed to get the molar mass of potassium nitrate, KNO3. So what you're going to want to do is find the mass of potassium, the mass of nitrogen, and then we need 3 oxygens. So you're going to take 3 times the mass of oxygen, and then once you have all of those written out, you'll simply add them up to get the overall molar mass. So pause this for a second and take a second and go ahead and do that, and then I will work it for you. Okay, so you've turned it back on. If you looked up potassium, you should have gotten 39.10. If you looked up nitrogen, you should have had 14.01. And if you looked up oxygen, you should have had 16. 3 16s are 48. So if I add those up, what I get is, let me take a second, 39.1 plus 14.01 plus 48 gives me 101.11 grams. And that's all there is to doing the molar mass of a compound. Now, when you look down at D, you may be like, whoa, what do I do with parentheses? So let me do one for you, not that one, because I do want you to be able to do that on your own. But let me do an example for you. Let's do aluminum sulfate. So what do we do with parentheses? Well, first of all, it's kind of easy to figure out how many aluminums I need, right? I'm going to need 2 aluminums. What happens with this 3 is it literally means I have 3 of whatever is inside the parentheses. The rule about subscripts is they apply to whatever is immediately in front of them. So this 2 applies to the Al, so I have 2 Als. This 4 applies to the oxygen, so I have 4 oxygens inside. And the 3 applies to the parentheses. So if we were using mathematical terms, we would say that the 3 distributes. So 3 times 1 sulfur, I need 3 sulfurs. 3 times 4 oxygens, I'm going to need 12 oxygens. So in order to do the molar mass of this, I'm going to need 2 times the molar mass of aluminum, which is 26.98. I'm going to need 3 times the molar mass of sulfur, which is 32.07. And then I'm going to need 12 times the molar mass of oxygen, which is 16. So when I do the math on this, I know that this is going to be 53.96. This is going to be 96.21. And this is going to be 192. So then I simply add those up to get my overall molar mass of this compound. So hopefully that helps you when you try to do barium phosphate down here. So I'm going to let you work through those, and then I'll come back and explain our next section. So hit pause and do that. So in our next section, we are now going to use those quantities to convert back and forth between grams and moles. Why do we need to do that? Well, grams are handy because we can measure them out on a balance, but it doesn't tell us the individual number of atoms or molecules. And elements and atoms and molecules react atom to molecule, atom to atom, molecule to molecule, not gram to gram. So let's see what I mean by that. So this is where we're going to go back to dimensional analysis, and it's very important that you mimic this process and that you don't do it another way just because you understand, oh, I can multiply or I can divide. You need to be setting it up because we are going to be using this in more complicated problem solving after Christmas. So let's look at 3A. On 3A, we are being asked if we start with 0.345 moles of manganese to convert that to moles. So remember for dimensional analysis that the unit you start with will always go on bottom. The unit you're converting to will go on top, and in this case, we're being asked to solve for grams. And what that relationship is the number for grams will always be whatever we got from the periodic table. You may remember on moles number 1, we looked at manganese. That's what's going to go with the grams. So for manganese, that's going to be 54.94 grams. And that's simply the amount of grams in 1 mole of manganese. So in order to do the math on this, I'm simply going to take 0.345 times 54.94. And how many significant figures did I start with? Well, I started with 3. Remember, leading zeros aren't significant. So I'm going to keep 3 in my answer, which will give me 19.0 grams. So let's review what we did to solve this. We started out with the number in the problem. We looked at our starting unit and made sure we put that on the bottom of the ratio to cancel. And then we put what we were solving for, which in this case is grams, on top. What number is always going to go with moles? 1. What number is always going to go with grams? Whatever we added up from the periodic table. So try the next few on section 3. Remember, it's gonna look very much like this every time. So take a second and solve those. And then I'll show you how to do the last type of problem. So on the last type of problem, you'll see that we are starting with grams and converting to moles. So this time, I'm going to want grams in the denominator and moles on top. What number did we say always goes with moles? 1. Where do we always get the number for grams? Periodic table. If it's an element, it's just its average atomic mass. If it's a compound, it's the sum of all of the atoms in that compound. Now, you may have noticed on the top one, with one exception, we'd already added those up. On the bottom one, the same thing goes. You've added those up on the left. So what am I going to do this time mathematically? Well, I'm going to take 2345 times 1 divided by 238.03. Remember that you're always going to multiply by the numerator and then divide by the denominator. And in this case, I had how many sig figs? 4. So I'm going to keep 9.852 for my answer. Remember that most of these molar masses you've already figured out on the left. So go ahead and work some more of number 4. I will also be working with you a little in class. So I just wanted to have this explained one time in a video so that you could refer back to it. And I hope that was helpful. Anyways, I'll see you in class today, and I hope you guys are all doing well.